Okay, so in the last class, we were talking about vector spaces. So vector spaces, as I told you, is collection of objects which satisfy these 8 properties. Okay, so objects are basically vectors. So examples of vector spaces, as we saw, were R square. Okay, so R square is a vector space. Okay, then R cube is a vector space. The set of all 2 cross 2 matrices is also a vector space. Okay, so if you collect all the 2 cross 2 matrices, it's going to be a vector space. So that will satisfy all these 8 properties. Now, in vector spaces, what are subspaces? So I want to look at what are subspaces. So subspaces, a subspace of a vector space is a non-empty subset such that any linear combination of vectors from the subspace stay in the subspace. Okay, so if you take any two vectors v1 and v2, so suppose there's some vector space v which contains some subspace S. Okay, so in this subspace S, if you take vectors v1 and v2 which belong to subspace S, which is basically a subset of the original vector space V, then this v1 and v2, they together satisfy a property that the linear combination of any two vectors here. So lambda 1 v1 plus lambda 2 v2 will also belong to S. Okay, so this is true for all v1 v2 belonging to S. So for all vectors v1 and v2 which belong to some subspace S, we have this property that lambda times v1 plus, sorry, lambda 1 times v1 plus lambda 2 times v2 must be equal to S. So at this point, it is necessary for you to understand that these lambdas are scalars. Scalars means, what is scalar? Scalar means a real number. It could be positive or a negative number, but it's a number, a fixed quantity. So that's what a scalar is. Whereas these v1s, vi's are vectors. Vectors meaning they are some components of the original vector space V that I'm considering. Now it depends what v1, v2 will look like, will depend on what is the original vector space. So they could be two-dimensional vectors, three-dimensional vectors, 2 cross 2 matrices. So they could be anything from the particular vector space. Okay, so for example, in the R square vector space, any line through origin is a subspace. So I'm saying that a line through origin in R square is a subspace. So my claim is that the line, any line, basically any line through origin. Let's start with 45-degree line. The 45-degree line through origin in R square is a subspace. So how do I check this? Okay, so the aim is to be able to check it. Back. So this is my R square vector space, and this is my 45-degree line through origin. Let's say this is the 45-degree line through origin. So my vector space V is R square. My subspace is all vectors of the format lambda comma lambda. Okay, the 45-degree lines equation is basically x equals to y, right? So the subspace is going to be lambda comma lambda. Okay. So I'm saying that so this subspace can also be written as lambda times 1. Okay, lambda times 1. For different values of lambda, you will get different elements in this subspace. For example, one of the subspace could be 1 comma 1. One of the vectors in the subspace could be 1 comma 1. Another vector could be minus 2 comma 2. So I'm looking at points which lie along this line x equals to y. So my claim is that this is a subspace. So the idea is that if I take any two vectors along this line and I take a linear combination of these two vectors, I should continue to get a vector which is again along this line. Okay, minus 2 comma minus 2. Yeah, sorry. Minus 2 comma minus 2. Okay. So what is so for all lambda 1 comma lambda 2, lambda 1 times, so this is my vector v1, this is my vector v2. Lambda 1 times v1 plus lambda 2 times v2 is going to be equal to lambda 1 times 1 1 plus lambda 2 times minus 2, which is going to be what? Lambda 1 plus minus 2 lambda 2 minus 2 lambda 2, which is going to be lambda 1 minus 2 lambda 2, lambda 1 minus 2 lambda. So as you can see, this x coordinate and y coordinate are still same. This is the x coordinate and this is the y coordinate. So they are still same. So it still is a point along this x equals to y line. I do not know where exactly will it be. It can actually be anywhere along the line. That will depend on lambda 1 and lambda 2 values. But the important thing is that its x and y coordinates are same. So this point still lies on the x equals to y line. All right. Is it clear?
Yes, sir.
My next example would be the line y equals to 2x is a subspace in R square. The line y equals to 2x is also a subspace in R square. So that's my next example. So what is a line y equals to 2x? So y equals to 2x is a line with 60-degree slope, right? So it would look like this. So what is the standard form of any vector on this line? Along this line, what would be the standard form in matrix format if you want to write? What would be the vector form of this, any vector along this line? Y equals to 2x line. Yes, Yuvakshi, can you give me the standard, the general form of any point along this line?
Sir, 1 comma 2.
Very good. 1 comma 2. 1 comma 2 is the vector, and then I multiply with any lambda. So lambda times 1 2. Okay, so this is the general form of any line. So if I take two vectors, v1 will be equal to lambda 1 times 1 2, and v2 would be equals to lambda 2 times 1 2. Okay, so you can write it like this, or alternatively you can basically write the vectors as, so any point will be of the format x comma 2x, right? So you can write any point as x comma 2x because y is equals to 2x. So you can write v1 vector as x1 comma 2x1 and v2 vector as x2 comma 2x2. So this time let's proceed with this example and see how I can show it. So lambda 1 times v1 plus lambda 2 times v2 is going to be equal to lambda 1 times v1 twice v1, sorry, x1 twice x1 plus lambda 2 times x2 twice x2. So that's going to be equal to lambda 1 x1 plus lambda 2 x2 and twice lambda 1 x1 plus twice lambda 2 x2. So this is basically lambda 1 x1 plus lambda 2 x2 times 1 2. So some constant k times 1 2. So this again becomes the point, becomes a point along the line y equals to 2x, right? Because this coordinate and this coordinate, they are still maintaining the ratio 1:2. So it is still along the line y equals to 2x. So we have all these lines as subspaces. So this is what characterizes as a subspace. The next example is all lines through the origin in R square are subspaces. All lines through the origin in R square are subspaces. So how do I prove this? So I'll start with some arbitrary line through origin. What is the formula of a line through origin in R square? Rityan, what is the formula of a line through origin in R square?
So is equal to mx.
Y equals to mx. Very good. So I can write v1 vector as x1 comma mx1 and v2 vector as x2 comma mx2. Okay. So it is some line through the origin. It can even be this negatively sloped line now. I don't care. It is some line through the origin. M can be negative. It can be positive. It can be any real number value. So now lambda 1 v1 plus lambda 2 v2. I just want to show that this thing is of the format xk comma mxk. If I can show this, then my proof is done. Okay, so I have to show that lambda 1 x v1 plus lambda 2 v2 is of this format. So what is this lambda v1 plus lambda v2? So this is going to be lambda x1 m lambda x1, so lambda 1 plus lambda 2 x2 m lambda 2 x2, which is equal to lambda 1 x1 plus lambda 2 x2 and m times lambda 1 x1 plus lambda 2 x2, which is basically lambda 1 x1 plus lambda 2 x2 times 1 and n. Okay. So 1:m ratio, I've obtained the 1:m ratio. So this is also a vector space. So all lines along the origin are vector spaces. Sorry, subspaces. Subspaces. So this is generally true. All lines through origin in Rn are subspaces. Not just R square, you take n dimensional vector space. You can take R cube, R4, R5. It's going to be subspaces. And not just lines, all objects, all infinite objects. Infinite objects meaning planes or three-dimensional structures. So everything passing through the origin, which has no restriction, which can go infinity in all directions, they are going to be subspaces. So this infinity is important thing. So I want to now check an example where something is not a subspace to understand what I mean. Because I've only given examples till now where everything is turning out to be a subspace. So I don't want to now give you an example where something is not turning out to be a subspace. So the positive x-axis is not a subspace. This is what I want to show. The positive x-axis in R square also. Okay, so the positive x-axis in R square. So this is what I'm talking about. Okay, so you take any two vectors v1. What is going to be a standard vector in along the positive x-axis, Kanishka? What is going to be the form of a standard vector along the positive x-axis in R square?
Sir, x comma 0.
Oh, very good. So I can write v1 as x1 0 and v2 as x2 0. Okay, so lambda1 v1 plus lambda2 v2, where x1 and x2 are positive, by the way. X1 positive, x2 positive. Okay, so lambda1 v1 plus lambda2 v2 will turn out to be lambda1 x1 plus lambda2 x2 comma 0. But lambda1 and lambda2 can be negative, where lambda1 comma lambda2, they can be any real entity. So this particular thing can even turn out to be negative. I can take lambda1 and lambda2 to be -1. So this thing turns out to be negative. So this becomes a vector along the negative x-axis. So this positive part by itself is not a subspace. Is this thing clear?
Yes, sir.
That just the positive part is not a subspace. The entire thing, when it is there, then it's a subspace. Okay. So let me ask you a question. A true or false? Okay, it's a true or false. True or false. The origin is a subspace in R square. The origin 0 0 is a subspace in R square. True or false? Yes. Is the origin a subspace in R square?
Sir, I guess yes.
It is very good. So it is because if you take lambda times 0, 0, it is continuing to be 0, 0, which is the original set that you started with. So any linear combination now the question is that there's only one vector in this subset. The only vector that I have is 0, 0. So I cannot check for linear combination, but then v1 and v2 can both be 0, 0. They both will be 0, 0. And then lambda 1 v1 plus lambda 2 v2 will be lambda 1 times 0, 0 plus lambda 2 times 0, 0, which will still be 0, 0, which is the subspace. So the origin is a subspace in R square, and not just in R square, in any Rn. In fact, the origin is the smallest subspace in any vector space. Okay, and remember, origin is also present when we talk about the origin. Origin is basically the zero vector. Okay, origin is same as zero vector. So if somebody talks about the origin when the vector space is 2 cross 2 matrices, what he's trying to say is the matrix 0, 0, 0. So that's the origin in the vector space of 2 cross 2 matrices. Because origin is nothing but zero vector. Origin and zero vector are the same thing. Okay, so sometimes they might use the word origin, sometimes they might use the word zero vector. So you have to be sure that you can be sure that they are the same thing. All right, so let's do a little more complicated examples. XY plane in R cube is a subspace. Okay, XY plane in R cube is a subspace or not. Okay, so the next example is the XY plane in R cube is a subspace. Okay, so standard vector in XY plane is going to be x1, y1, 0. Because XY plane means what? XY plane means its Z coordinate must be 0. X and Y can be anything. Its Z coordinate must be 0. So when I take lambda 1 v1 plus lambda 2 v2, it's going to be equal to lambda 1 x1 plus lambda 2 x2, lambda 1 y1 plus lambda 2 y2. The Z coordinate is going to be 0 because it's basically lambda 1 0 plus lambda 2 0. Okay, which is basically x hat, y hat, 0. So this is still in the xy plane. So the xy plane, it's not a line, it's a plane, but it's an infinite entity passing through the origin. Okay, the origin must be present in every subspace. Okay, so here's another important thing. The origin must be an element in every subspace. The origin necessarily must be an element in every subspace. The proof is very straightforward. Let v1 comma v2 belong to some subspace, then lambda 1 v1 plus lambda 2 v2 must also belong to the subspace. That is a property of the subspace. But if lambda 1 equals to lambda 2 equals to 0, because these lambdas, they can be any real entity. So if you take both of them 0, then lambda 1 v1 plus lambda 2 v2 becomes the 0 vector in the particular vector space. So this implies that 0 vector must be contained in the subspace. So something is a subspace only if it contains the zero vector in it. Otherwise, it's not a subspace. Okay, so this is an easy check. If somebody gives you a complicated example to ask you if something is a subspace or not, just check if that particular definition contains the zero vector in it or not. So let me give you another example to clarify this point. So consider these two examples, example 1 and 2. The set of diagonal matrices are in diagonal matrices in 2 cross 2 vector space are a subspace. Example 2, the set of diagonal matrices with non-zero diagonal entries. Sorry, the set of upper triangular matrices. Sorry, upper triangular matrices with non-zero uh, entries above the diagonal in 2 cross 2 matrices in 2 cross 2 are a subspace. Okay, so in the first example, you just have set of diagonal entries with some x, 0, 0, x type form. Here you have upper triangular matrix with some, I should not write x, I should write x1, x2 or x1, y1. And this would be x1, y1, 0, z1 with y1 strictly positive. Okay, so this is some vector v1, this is some vector v1 here. Then a vector v2 here would be x2, 0, 0, y2. And the vector v2 here would be x2, y2, 0, z2 or y2 positive. Okay, so the crucial thing in definition of example 2 is that non-zero entries above the diagonal. So these entries above the diagonal, they have to be non-zero. So then if I take 0 times v1 plus 0 times v2, basically lambda 1 and lambda 2, 0, I get entry 0, 0, 0, which qualifies as diagonal matrices. What are diagonal matrices? Diagonal matrices are matrices where everything except the diagonal is 0. Everything of diagonal is 0, is null. Whereas in this case, when I take 0 times v1 plus 0 times v2, again I'll get 0, 0, 0, 0. But now this entry has become 0. So this particular entry, 0 vector, it does not belong to the set which I was initially looking at. The set was upper triangular matrices with non-zero entries above the diagonal. But here I get a 0 above the diagonal. So that's not allowed. So I get an element which does not belong to the space which was given to me. So this implies that this is not a subspace. So this is a very easy thing to check if something is not a subspace. Okay, this does not prove that something is a subspace. I hope this point is clear to everyone. You can use it to reject something not being a subspace, but you cannot use this as a proof for something being a subspace. Okay. So the idea is that a subspace must contain the zero vector, but just because something contains the zero vector does not make it a subspace. So we saw the positive x-axis thing. The positive x-axis, if you include zero in it, it is still not a subspace. Okay. So a subspace must contain the zero vector, but the converse is not. Okay, so it should contain the zero vector, but the converse may not be. So let's quickly check some more examples. The space of vectors. All right, why don't you guys work out these 4 examples? Yeah, work out these 4 examples for me and tell me which of them are subspaces or not. Okay, so your final answer should be, let's say you find out 2 and 3 are subspaces, your final answer just be 2 and 3. Okay, so that's what I want. Okay, the first is x positive, y positive. So it's an infinite plane, but only the first quadrant. It's basically the first quadrant. Okay, x positive, y positive. X greater than equals to 0, y greater than equals to 0. Okay, so it's basically this region, including the axis and the origin. Okay, so the origin is included. So I cannot use rejection technique here. But I can take 2 vectors here, v1 and v2. Now, what are v1, v2 going to be? So v1 is going to be x1, y1 for x1 positive, y1 positive. v2 is going to be x2, y2. But lambda times v1 plus lambda 1 v1 plus lambda 2 v2 is going to be lambda 1 x1 plus lambda 2 x2, lambda 1 y1 plus lambda 2 y2. Now for lambdas negative, both these quantities can be negative if lambda I less than 0. So if both lambdas are negative, I could have the linear combination of these 2 vectors as negative. So just take lambda equals to -1. Okay, take lambda 1 equals to -1. Okay, so what this becomes is minus v1 minus v2. So that becomes, you can take any value to disprove if something is a subspace or not. So these 2 quantities become strictly negative. Right. So what I get is that the linear combination will be somewhere here. Okay, along this direction. So it's not in the first quadrant. Okay, so it is not in the first quadrant. So this thing is not a subspace. Let's look at the second example. The subspace xy greater than equals to 0. So again, xy greater than equals to 0 is can be both in, yeah, so it will be vectors here and here. So this is xy, sorry, xy greater than equals to 0. So it is basically first and third quadrant. This region and this region. Okay, so I can take 2 vectors here, v1 and v2. All right. Now the idea is a linear combination of these two vectors. Does it continue to be in the yellow region or not? So let me show this with the help of an example. So this is a little tricky one. So lambda 1 is, let's say, 3 comma 1, and lambda 2 is equals to, let's say, 2 comma 2. Sorry, minus 2 comma minus 2.
So V2.
Sorry, V2. V2 is minus 2 comma minus 2. Now V1 plus V2 should also belong in the subspace. But when I do V1 plus V2, it just becomes 1 comma minus 1, which is here. Okay, so this set, which was xy greater than equals to 0, this set contains the origin. Okay, but it is still not a subspace, because you saw that for V1, V2 in the subspace, V1 plus V2 does not belong to the subspace, right? So this point is heading in this direction, 1 comma minus 1. So x into y is not greater than equals to 0. X into y is negative. So this is not in the subspace. This is not in the subset. So that's why this thing is not a subspace. Okay. So 1 is not a subspace, 2 is also not a subspace. Now let's look at 3. The space of lower triangular matrices in 3 cross 3 vector space. So that's third example. All the lower triangular matrices in 3 cross 3. So lower triangular matrices means something, 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 0, something, something, 0, 0, something. So these are lower triangular matrices. So you can write some values here. A1, B1, C1, D1, E1, F1. Where each of these entities can be greater than equals to 0. Okay, lower triangular means everything below the triangle, below the diagonal is 0. So lower triangular is everything below the diagonal is equals to 0. So these three entities must be 0. The remaining can be anything. So I'm just going to focus on these three entities. So these three entities must be 0. So when I do V1 plus V2, so similarly you can write V2 vector is going to be A2, B2, C2, 0, D2, E2, 0, 0, F2. So V1 plus V2 is A1 plus B1, sorry, A1 plus A2. Or lambda V1, if you want to do it lambda V1 plus lambda V2, you can even do that. Lambda V1 plus lambda V2, lambda 1 V1 plus lambda 2 V2. This is going to be lambda 1 A1 plus lambda 2 A2. Then lambda 1 B1 plus lambda 2 B2, lambda 1 C1, lambda 2 C2. Here it's going to be lambda 1 0 plus lambda 2 0. So that's going to be 0. Here it's going to be lambda 1 0 plus lambda 2 0. So in this case, again, I'll go get 0. Right? And finally, here 0 plus 0. So in this space, again, I'll get a 0. In the remaining spaces, I get anything. If these three entities are 0, then everything below the diagonal is 0. So this is still a upper triangular. Oh, sorry. I wanted to check it for upper triangular. I checked it for lower triangular. Sorry, I wanted to check it for lower triangular. I did it for upper triangular. Sorry. Let me change the question. So let's say I did it for upper triangular, but the results are going to be the same. Yeah, exactly. So you can extend the similar logic to lower triangular matrices. But by the way, these are upper triangular matrices. Upper triangular matrix means everything below the diagonal is 0. Okay, so please don't get confused with the names. The word upper triangular means that you have to focus above the diagonal, but actually you have to focus below the diagonal. Upper triangular means below the diagonal 0. Okay, so this is still a upper triangular matrix. Okay, so similar logic will hold for lower triangular matrices. So this is going to be a subspace. And finally, symmetric matrices in 3 cross 3 space. So how do I define symmetric matrices? Anyone?
The
How can I write?
transpose will be same.
Yeah, but if I want to write a general formula for vector v1, then what can I write it as?
So Aij equal to Aji barring
Give me this
the
3
diagonal
plus 3 thing.
elements.
Sir, A, D, E,
A, D, E.
D, B, F, E, F, C. D, B, F, D, B, F,
DBF,
and E, F, C.
EF. Very good. So what you're saying is that these three entities are independent. These two are same. These two are same. And so these two are same. And finally, these two are same. Okay, so it's like a mirror image of each other if you put a mirror along the diagonal. So these are symmetric matrices. So obviously, I'll put one everywhere when I want to talk about V1. Okay, let me remove these colors. And V2 matrix is similarly A2, D2, E2, D2, B2, F2, E2, F2, C2. Okay, so when you take lambda 1 V1 plus lambda 2 V2, if you take this matrix, then in this position and in this position, what you will get is you get something here. I don't want to worry about it. The important thing is lambda 1 D1 plus lambda 2 D2. This is what you get here. And what you get here is also lambda 1 D1 plus lambda 2 D2. So these two entities are going to be equal. And the same will hold for positions like these and then E as well. Okay, so you will get similar entries at Aij, Aji. Whatever you're saying is correct. Aij equals to Aji, A transpose is equals to A. All that definition is okay. But when doing this problem, I want to look at what kind of, how can I define my vector space so as to get this final proof. So when I do this, I'll see that this is also a symmetric matrix. So that's why this is also a subspace. Okay, so third and fourth are subspaces, first and second are. All right, so now obviously I did a lot of work with subspaces. Then the question is, why am I doing so much on subspaces? Why is it necessary? So subspaces help me find the complete solutions for a given linear system of equations. So remember when I was talking about a system of equations Ax equals to B, suppose you are solving this system of equations, you can get three possible outcomes. You can get no solution, you can get infinite solutions, or you can get a unique solution. In the first lecture, we focused on getting a unique solution and we looked at Gaussian elimination. We saw how to solve this unique solution thing. We left these no solutions and infinite solutions bit at that point of time. So now we are going to focus on, and subspaces and our knowledge thereof is going to help us find it. All right, so before being able to get to the complete solution, we still have to develop a few concepts. So one major concept is column space of a matrix. So the column space of a matrix A is the space of all vectors formed by the linear combination of the columns of a matrix. Okay, so suppose this is vector a matrix A, this you call as vector V1, this as vector V2, right? So you can use V1 and V2 to get all sorts of matrices. All sorts of vectors. So for all lambda 1 comma lambda 2, this is going to be the column space of A. So column space of A is basically the set of all vectors which can be formed using linear combination of the columns of any vector. So suppose your vector A is 1 0 0 0 1 0 0 0 0. So this is your V1, V2, and V3. V3 is basically 0 vector. So if I look at column space of A in the XYZ vector space, that is the RQ vector space, column space of A is going to be the XY plane, right? Because V1 is 1 0 0, V2 is 0 1 0. So lambda 1 V1 plus lambda 2 V2 plus lambda 3 V3 is going to be all vectors of the format lambda 1 lambda 2 0, which is basically XY plane. Is this thing clear?
Yes, sir.
Now, if I remove V3, if I just take this vector, even in that case, it's going to be the XY plane in the R cube vector space. The vector space is still going to be this, the subspace is still, the column space is still going to be this. Okay. So that third vector was really very redundant. It was not adding to anything. On the other hand, if I add a vector 1 1 0, the vector space is still going to be the XY plane. Okay, so now this is going to be lambda 1 plus lambda 3, lambda 2 plus lambda 3, 0. This is still the entire XY plane. You can generate the entire XY plane. You can reach any point using some, suppose I want to prove that any point x comma y, comma 0 lies in the column space of A. So I just want to make sure that I take lambda 1 and lambda 2 and lambda 3 values in such a way that lambda 1 plus lambda 3 must be equal to x, and lambda 2 plus lambda 3 must be equal to y. Okay, so basically these two terms must add up to x and these two terms must add up to y. So if I can ensure lambda 1, lambda 2, lambda 3 values in such a way when this is true, I can reach any point xy in the entire xy plane. So the entire xy plane is basically covered here. That's what I'm trying to show, that the entire xy plane is covered here. So this column space will still be the entire xy plane. But if I take v3 vector as 0 0 0 0 1, then column space becomes entire R. Column space becomes entire R. Okay, now this is going to be lambda 1, lambda 2, lambda 3, which is entire R cube. So the column space becomes entire R cube. So it will depend on what the column spaces will depend on how these vectors, what these vectors are going to be. All right. But one thing is certain, that the vector space of which the column space is a part of if the matrix A is M cross N. So this vector space will always be R to power M. It depends on the number of rows. So I can take a fourth vector here, 1 0 1, and maybe even a fifth vector 1 1 0. I still have 5 vectors, 1 2 3 4 5, but each of these vectors are still from R cube. So any linear combination of them will continue to be in R. All right. So you can take two vectors or you can take five vectors. Or you can take 100 vectors. As long as the number of rows is 3, the column space will always belong to R. Okay, so the column space will always belong to R. Column space will be always a subset of RQ or R to power M if you have a general M cross N matrix. So here you have two columns, but the number of rows is 3. So the column space will be a subset of RQ. Okay, so column space of A will be a subset of R. Now the column space contains all matrices of the form B such that for some U and V, U times vector 1 plus V times vector 2 becomes equal to B1, B2, B3. All right, now this thing can be restated as the formula that my matrix A times X becomes equal to. So this thing essentially becomes AX equals to B, which brings me back to this particular thing that AX equals to B will have a solution either infinite or unique only if B belongs to column space of A. So when does it have some solution at least? So it will have some solution only if the coefficient vector B, it belongs to column space of A. Okay, so coming back, just to give a recap, what I'm saying is that if this is my V1 and V2, then all vectors B which belong to column space, will have some, instead of lambda 1, lambda 2, you have U and V. So instead of lambda 1, lambda 2, you have U and V, such that this vector B is equals to U times V1 plus V times V2 for some U and V. This will be true if B belongs to column space of. So the idea is that my vector B should belong to the column space of A in order for it to have one solution or infinite solutions. If, on the other hand, B does not belong to column space of A, then AX equals to B has no solution. Okay. So to give a quick example here, suppose your matrix A is 1, 0, 0, 0, 1, 0, 0, 0, 0. Then for which B vector does AX equal to B have no solution? Okay, so your options are option A 3, 4, 0, option B 5, 0, 4, option C -7, 0, 1, and option D is 3, 0, 1, -1. Multiple can be correct. So for which of these options will AX equals to B have no solution?
Sir, B, C, and D.
B, C, and D. That's actually correct. So the idea is that I saw that for this particular matrix, the column space is XY plane. So any vector in XY plane will have solutions, but anything off the XY plane will not have solution. So Z coordinate needs to be 0. But here, Z coordinate is non-zero. So you will not have any solutions for B, C, and D. Obviously, I mean, you would be very lucky if you get a question so simple as this one. Obviously, we are going to look into how to resolve the complicated cases. But here the aim is to be able to understand what I'm trying to say, that any B vector which cannot be reached using a linear combination of these column vectors will have no solution for Ax equals to. Okay, so how to do that for complicated cases is going to be something we are going to look at subsequently. But here I just want to focus on you understanding the concept of what is the importance of column space and how it is related to which of the three cases I'm going to end up in. Okay, at least it can demarcate the cases of no solution with at least one solution. Now, a very important property, the column space of A is a subspace. Okay, I know that column space of A is some subset of the Rm vector space. Okay, so what I know is, what I've already told you is that the column space takes vectors from matrix A. So what I know is that column space of A is a subset of the Rm vector space. But what is actually true is that column space of A is not just any subset, it's a subspace of Rm vector space. So basically what I'm saying is that if B1 comma B2 belong to column space of A, then lambda 1 times B1 plus lambda 2 times B2 also belong to column space of A. This is the definition of a column space, right? Sorry, of a subspace. If any two vectors belong to a subspace, then a linear combination of these vectors should also belong to the subspace. So let's say I want to prove this. Okay, this proof is important. They can ask you in the subjective part of IS. Okay, so how do I prove this? Okay, so I already know that B1, B2 belong to subspace. So Bi belongs to the column space of A. Implies there exists some xi such that A times xi is equals to Bi for all I belonging to 1 comma. This is how you can write a very nice statement. You don't have to write it for B1 and B2 separately. I'm saying that for all Bi, for all I where I can be 1 or 2, Bi belongs to column space implies there exists xi such that A times xi is Bi. So this statement in itself means two statements. That there exists x1 such that A times x1 vector is equals to B1 vector, and there exists x2 such that A times x2 is equals to B2. Okay, this vector may or may not be written in theory. Okay, so whenever it's not written, even in that case, you have to assume that they are vectors. This is something we talked about in linear algebra. Everything is vector or matrix. Okay, the scalars are going to be represented by lambda, nu. The Greek letters are going to be scalars. The That's the convention. Goes without saying. Lambda, nu, alpha, beta, gamma, they are all scalars. All the English alphabets, they are going to be vectors or matrices. So generally small alphabets, small letters, vectors, capital letters, matrices, Greek letters, scalars. So that's going to be the convention. So these two statements together written here. So if you write this statement, you don't need to write either of these two statements. So that's done. Basically, for every bi vector, I have some xi, which is a solution to axi equals to bi. Okay. So now what I need to show that there exists some x hat such that ax hat is equals to lambda times lambda 1 b1 plus lambda 2 b2. Basically, I want to show that lambda 1 b1 plus lambda 2 b2 also belongs to subspace, column space, which implies that there is some solution to ax equals to lambda v1 plus lambda 2. Okay. Now, in order to show this, remember that x1 is a solution to ax1 plus b1. So, lambda x1 plus, so lambda 1 x1 plus lambda 2 x2 times a vector is going to be a times lambda x1 plus a times lambda x2. So this comes from the distributive property of matrix multiplication.
The lambda 1x1.
Yeah, lambda 1 x1, lambda x2. Thanks. So this becomes lambda 1 times a x1 plus lambda 2 times a x2. Since lambda is a scalar, I can do this. Remember, this can happen only because lambda is a scalar. Okay. If you have matrix multiplication, ABC is not equal to BAC. ABC and BAC might not even make sense. Okay. BAC might not even exist. So this can happen, this step can happen because lambda is a scalar. Now AX1 is equals to B1 and AX2 is equals to B2. So what I have is A times lambda x1 plus lambda x2 is equals to lambda b1 plus lambda b2. So this is the desired solution which I wanted. A times x hat is equals to lambda b1 plus lambda b2, which basically implies that there exists a solution for ax is equals to lambda b1 plus lambda 1 b1 plus lambda 2 b2. I'm not interested in finding the solution. Right now I'm content with the existence of a solution, because if a solution exists, it implies that this thing is also in the column space. So how will you show if anything is a subspace? Any set is a subspace. So step one is take any two arbitrary vectors in the given subset. So in this case, we took B1 and B2 belonging to column space of A. Step two is take linear combo of the two vectors. That's what we did when we took lambda 1 B1 plus lambda 2 B2. And step three is simply show that the linear combination also lies in the subset. This is what we showed when we showed that lambda 1 b1 plus lambda 2 b2 also belongs to column space of A. Okay, so these are three generic steps to show that anything is a subspace. Okay, and we followed the same ideology. Now, the reason I'm giving this entire algorithm to you is there's going to be one more thing which we are going to study hopefully today, wherein you would be required to show that by yourself, you have to show that it is a subspace. All right, so that was the proof which I have given here. So this is another way to show that something is a subspace. So this is a second way to show that something is a subspace. In this case, it's a two-part thing. You have to show two things. Suppose B1 and B2 lie in column space. So you have to show B1 plus B2 lies in the column space. And if B lies in column space, you have to show that lambda times B also belongs in column space. So this is another way to do the same thing. So the one I did is one large proof. This is a two-step thing in which you do two smaller proofs. So if both these things hold, even then it is correct that the given thing is a subspace. Okay. All right. So remember, column space of a matrix is all vectors B for which Ax equals to B has a solution. So let me write it down for you very clearly. The column space the column space of a matrix A is all vectors B such that Ax equals to B has at least one solution. It is a collection of B vectors. Okay, it is a collection of B vectors. Okay, so let me come back to the whole discussion about dimensions that we were having in the previous lecture. Ax equals to B. So column space is collection of B vectors. Suppose A is M cross N. So what should be the dimension of X and what should be the dimension of B? Come on, dimension of X.
N cross M.
No,
And M.
it's a vector. It's a vector. It's a vector.
So
R
n
raised
cross
to the
1.
power M.
I'm asking, yeah, I'm asking dimension. So yeah, you're saying R to the power?
M.
Yes, you are actually. M for Madras?
Yes, sir.
No, because
Sorry,
then it
N.
is, yeah, you cannot
Sorry,
keep changing it every time. There are
sorry,
only two.
sir.
Okay, so
Column
this has to be N cross.
rows. Yeah, R to the power.
And what about B?
M cross 1.
M cross 1. Okay, so that's what I told you initially, right? The B vectors are in the Rm space where M is the number of rows. It doesn't depend on how many column vectors you have. Okay, the column space actually depends on the number of rows in the matrix and not on the number of columns. Okay, ironic. Anyway, let's jump to the next topic, which is going to be very similar. That is null space of matrix. Now, what is null space of matrix? So, null space of a matrix is, so column space was the set of all B vectors such that Ax equals to B had a solution. The null space is set of all solutions X which solve Ax equals to 0. Okay, so now for the null space, I'm not going to even focus on B. What is B? I'll forget about B altogether for the time being. I'll just say that for any matrix A, I want to solve Ax equals to 0. Remember, again, vectors. Okay, 0 means 0 vector. Okay, so if this is M cross N, this has to be N cross 1 for the multiplication to make sense, and this has to be M cross 1. So this is going to be a sequence of m zeros. That is what I mean by ax equals to 0. So all x which solve the above equation belong to the null space of A, the null space. Okay, so all x vectors which solve the above equation, that is x equals to 0, this is the equation, they belong to the null space of. So it's going in the Rn space. Again, x is n cross 1. So the null space of A is a subset of the Rn space. And the column space of A was a subset in Rm space. A very important thing, because these are simple things which they can ask you in the objective part. Now, null space is a subspace. So this is what I want you guys to do using the algorithm which I had told you about. So let me just copy this section from here. So I want to show that the null space is also a vector space. So why don't you guys tell me the first step, second step, third step? So first step, yeah, Vinay, how do you go about the first step?
So define two vectors v1 and v2.
Which satisfy what property?
That when we do combinations, we get a null space vector.
No, you cannot write such vague proof. You'll get 0 straight out. V1 and V2 should satisfy some property. What should be that property?
That
What am
they
I
belong
trying
to this column space of R. Rm.
I'm not talking about column space. What is this written here? What have you written here? Can you read this?
Null space.
Yeah, so forget about column space. So if V1 and V2 belong to the null space, what property should they satisfy?
A vector into multiplied into a matrix will give you a null set.
What? Can you come back?
When multiplied into when we multiply
Can you
it
give the
into
equation? You have A here. Just give me the equation. Why are you trying to? This is not an essay competition, by the way. Right. So give me the equation. Can anybody else tell me what property V1 and V2 satisfy?
can I try?
Yeah.
A
Any
into lambda 1 x1 plus A into lambda 2 x2.
What is X1?
X1
You just
is
told me V1.
the x component of V1.
Okay.
Yeah, X1.
A
Yeah,
into
A into V1
what?
x1 y1. That would be a vector, right?
Till how much should I go? X1, Y1,
Till m.
till M. X1, Y1, let's say there is till M, till M, N, right? So Z1 till N.
Yes.
n rows. Okay, so what happens to this thing?
Or we multiplied into lambda.
Okay, lambda times a into this thing.
And if we can show that it is 0, then
I'm not,
it,
I mean, you want to show this to be 0. Okay.
yeah.
No, I mean, the initial thing is you don't have to show anything in the first step. The first step is you want to define two vectors which satisfy some property. Can anybody tell me what property should V1 and V2 satisfy to begin with? V1, V2 belong to null space of A. So what property should they satisfy in equation terms? What is the property which they should satisfy? Come on, Yuvakshi, what is the null space? What is the property of a null space, Yuvakshi?
Sir, elements in so B1, comma B2 belongs to null set A, which are the
Okay.
element of
So
No, I'm
V1 and
asking
V2
if
both are null vector. Zero.
no, what is written here? Just focus on this equation. This is the only equation you get to work on. Okay, so A times V1 must be equal to 0 and A times V2 must be equal to 0. These two properties need to be true. V1 and V2 are null space. What is the definition of null space? A null space is a vector such that AX equals to 0. All vectors, all X vectors which solve the above equation belong to null space. So my aim was take two vectors in the null space. The aim is to show that the null space is a subspace. So I take any two vector in the subspace, in that particular subset, that is the subspace. So V1, V2 belong to null space, which basically says that A times V1 is 0 and A times V2 is 0. Is this clear?
Yes, sir.
Okay,
It's
sir.
not so difficult. Okay, it's very easy. Null space, subspace is very easy. I'm just giving the entire algorithm also. I mean, this cannot get easier than that. I mean, find the entire set of all coaching classes and find me a teacher to break it down more easily to you and give you back your entire money. I mean, I cannot tone it down easier than this. Right? Second, linear combo. So what is the linear combo of these vectors?
Lambda V1 plus lambda.
You have to
Plus
speak loudly and speak the entire thing. I mean,
so lambda 1 V1 plus lambda 2 V2.
okay. So I have to show, so this third step is I have to show that the linear combination is a null space. This is third space. Which means what? That A times lambda 1 V1 plus lambda 2 V2 must be equal to 0. Right? This is what I have to show. So V1 V2 belongs to null space. I have to show this thing. So when I open up the bracket, this will just be lambda lambda 1 AV1 plus lambda 2 AV2. I have to show this to be true. Okay, this is not given to be true. I have to show this.
Say AV1 and AV2 is 0.
Yeah. So lambda 1 0 plus lambda 2 0. So that is 0. So this proof is done. Okay, so that's very simple. So that null space is a subspace. See, I'm going very slow with you guys, so that's going to take time to complete the syllabus. But I don't want to rush here because you guys are taking, because I don't want to like rush through things and then you guys are not able to absorb it, right? So you'll have to be more patient because I'm also being more patient. So what's going to happen is that we are going to have to take some more extra classes. Things are not going to get wrapped up like immediately because these are important things which I don't want to rush over. Okay, so but you have to be regularly and you have to start attending classes regularly, so that I know, because if you don't attend and I teach to a blank screen, what happens is I don't even know what type of things you have a problem with. So if I don't understand you as a student, I cannot address those issues. So it's good that you guys are attending. My word is out for those who are basically watching the recorded videos, that if you attend the lectures, I can basically understand. Usually I just breeze through these topics, but if students have issues in these topics, I'll take more time, but that can only happen if more students attend the live classes. Anyway, so the null space is a subspace. So that proof is done. Here, the proof is done in two parts. Okay, so my recommendation to you is I've done it in one way in the classes. The other way is done in the notes. So you go through the notes for both these proofs, for the null space as well as subspace. So that will basically give you an idea into the second type of proving. All right. Okay, so that wraps up null space of a matrix. Now let's look at independent vectors. So suppose we have to solve for this ax equals to 0. All right. So it is easy to see that the only possible solution is x equals to 0. Okay, so ax equals to 0. By the way, ax equals to 0. This thing always has a solution. The trivial solution is x equals to 0. Okay, again, when I write x equals to 0, vectors, not scalars. Okay, it means x vector is a 0 vector where this 0 vector is a m cross 1 vector. Okay, so I'm repeating it again and again because the problem is if I don't write this sign, we are hardwired to assume that this x is some scalar and it is equal to 0. Okay, so that's why I keep saying it again and again, that when the context is matrices, everything is vectors. Only the Greek letters are going to be scalars. Okay, so this trivial solution will always exist. For x equals to 0, this thing will always have a solution. So the null space of a matrix always has 0 vector in it. Okay. Now the question is, can there be solutions other than this 0 vector? 0 vector is always a solution for any ax equals to 0. Give me any a vector, any matrix A, ax equals to 0, x equals to 0 will always be a solution. That part is the trivial solution. The interesting part is there some vector other than the trivial solution which can be the solution for ax equals to 0? So for this particular matrix A, the only solution is x equals to 0. Now this happens because the column vectors of matrix A are independent. Okay, so what are the column vectors here? 1, 5, 2. This is my v1, and v2 is 0, 4, 4. So these two vectors are independent vectors. I'll come to the definition of independent vectors and everything, but right now I want to make a point that this is a situation where you have only the trivial solution as the possible solution for ax equals to 0. Let's look at this matrix now. Now v1 vector is 1, 2, 2, and v2 vector is 2, 4, 4. Okay. So this ax basically becomes u times v1 plus v times v2. So this should be equal to 0, 0. Now notice that if I take u equals to 1 and u equals to 2 and v equals to -1, this u times v1 becomes 2, 4, 4, and v times v2 becomes -2, -4, -4, which becomes 0, 0, 0. So 2 minus 1 is a solution to Ax equals to 0. I'm trying to solve Ax equals to 0. So 2 comma minus 1 is also a solution to Ax equal to 0. Now, so obviously, in this case, the columns were in the ratio 1:2, so it became very evident. Doing it for more complicated cases is something I'm going to see later on. But here the important point is that the column V2 is just twice of column V1. So they are sort of dependent on each other. V2 is equals to twice of V1. That is the dependency. V2 equals to twice of V1. So they are sort of dependent on each other. Okay. Now, coming back to the original vectors, 1, 5, 2, 0, 4, 4, I saw that the only solution possible was in 1, 5, 2 and 0, 4, 4, the only solution possible was the trivial solution. Now I add another column V3, which is basically V1 plus V2. So I just add the first two columns and generate a new column. So it's going to be 1, 9, 6. So the third column is generated using the first two columns. So it is dependent on the first two columns. Okay, so that's the dependency which connects these three column vectors. So the vectors are not independent because they are dependent on each other. So now look at this matrix which I've generated using V1, V2, V3, 1, 5, 2, 0, 4, 4, and 1, 9, 6. Okay, so 1, 5, 2, 0, 4, 4, 1, 9, 6. So this is the matrix I have. I'm trying to solve Ax equals to 0. So U times 152 plus V times 044 plus W times 196 must be equal to 0, 0, 0. Now you can take U as +1, V as +1, and W as -1. Okay, so UVW equals to 1, 1 minus 1 is going to solve this system of equation. So 1, 1 minus 1 belongs to null space of A. So what I want, the story is when I had just these two columns, the only possible solution for Ax equals to 0 was 0, 0. But when I add a third column, which is dependent on the first two columns, I start getting new solutions. Okay. Keep in mind that 0, 0, 0 is always a solution. Let me call this matrix as A prime. Let me call this as A prime because it's generated from A, but it's slightly different. So that's why I'm calling it A prime. So null space of A prime 0, 0, 0 will always be a solution for null space of A. Okay, so there's no issue there. The question is, are there solutions? When do we get solutions other than the trivial solution? The trivial solution being 0, 0, the 0 vector. So when does the null space have vectors other than the trivial solution? So that becomes a question. So that happens when the column vectors are dependent on each other. Okay. So if the column vectors are independent, it implies that null space of any matrix A is basically equal to just the same. So not just 1, 1, minus 1 in this new matrix, which I called A prime earlier, or you can call it B. All vectors of the form T, T, and minus T are going to be in the null space of A. So basically, B times T, T minus T is going to be 0, 0 for all T values. All T values, this is going to be. All right, I'll come back to this problem if I am unable to do it on your own. But I want to complete linear independence. What is linear independence? So I introduced some definition of independence and dependence. So the definition is that if the column vectors are sort of dependent on each other or drawing from each other, then they are dependent vectors. If they are not related to each other, they are independent. But linear independence has to be firstly defined. So the definition is that let V be a vector space such that vectors V1 to Vm belong to this capital V. A linear combination of these vectors is a summation of the form summation alpha I Vi. So I have some combo of vectors V1 to Vm, and I define a linear combination which is summation alpha I Vi. So this linear combination is called trivial if all the alphas are 0. Okay, the sum of a trivial linear combination has to be 0. A system of of vectors V1 to Vm is called a spanning system or a complete system in V. So these are different definitions of what of words. Words you need to know. So V1 to Vm is called a spanning system or a complete system if any vector in V can be represented as a linear combination of this system of vectors. Okay, so in the complete system capital V, if small vector small v, that is V1 to Vm, they can be taken together and the linear combination can be used to span the entire system, that is the entire Rn can be recreated, then that becomes a spanning system. Okay. So what is the meaning of this? That you take any vector in the vector space, you can find scalars beta 1 to beta m such that the vector V is a linear combination of these vectors in the spanning system. Okay. So for example, suppose you are talking about the R cube vector space. So suppose your vector space V is R cube. Then vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 is a spanning system. Because any vector can be represented as a linear combination of these three vectors V1, V2, V3. Any vector in R cube can be represented as a linear combination of these three vectors, right? Suppose I add another vector to this 1, 1, 0 as V4, it will still remain a spanning system. Okay, I can still reach all the vectors. Even these three vectors are sufficient to do it. You add another vector, no problem. Okay, you can add a vector 0, 0, 0 to it, no problem. As long as three people are taking the burden, additional people are not going to harm you. It will still remain a spanning system. Okay, so a spanning system is when the vectors together have the potency or the capability to reach any point in the entire vector space. Okay, so any point in the entire vector space can be reached using these vectors. So then the vectors are called a spanning system. So such a system of vectors could therefore span the complete vector space. You can reach any vector. So if you just give me these three vectors V1, V2, V3 and ask me to reach some point, let's say 9, 11, minus 13, I can say that this is just 9 times vector V1 plus 11 times vector V2 plus minus 13 times vector V3. plus 0 times vector v4. So I can use the 4 vectors in order to reach any point, not just 9, 11, minus 13. Give me any point. I can use these 3 vectors to reach any point in the vector space. Now, spanning system of vectors is called a basis for V if any vector small b can be represented in a unique linear combination. Okay. Now, notice that another way to use v1, v2, v3, v4 to reach 9, 11, minus 13 would be 9, 11, minus 13 is equals to 7 times v1 plus 9 times v2 minus 13 times v3 plus 2 times v4. Okay, so this is basically 7 times 100 plus 9 times 010 minus 13 times 001 plus 2 times 110. So when you add these up, you will get 7 plus 2, 9 plus 2 minus 13 plus 0. So that is 9, 11. So what I'm saying is the same point V, which is 9, 11, minus 13, can be recreated using a linear combination V1, V2, V3, V4 in multiple formats. Okay. But if I restrict you to using just V1, V2, and V3, then 9, 11, and minus 13 can be represented in a unique way, which is 9 times V1 plus 11 times V2 minus 13 times V2. So both V1, V2, V3 and V1, V2, V3, V4, they are both spanning systems. But the difference is that with V1, V2, V3, any point can be reached only in a unique way. Whereas with V1, V2, V3, V4, you can have multiple combinations to reach a point. Okay. So when a spanning system can be used to reach some point only in a unique way, then that spanning system is called a basis. So a basis is a spanning system, such that any vector V belonging to vector space can be represented in a unique way. So there will be a unique way in which you can represent any vector in the vector space if it is a basis. Now, if you have a Rn vector space, then number of vectors in the basis will always be equal to n, and number of vectors in a spanning system will always be greater than or equal to n. Okay, so this is not a definition, but this is a property that if you have a n-dimensional vector space, see, I can just give you the final results and breeze over it. But the point is, you should know these inner details. That the actual definition is of a basis is a spanning system in which any vector can be reached in a unique format. Now, this is something which can be asked, like they can give you 4 options and say which of these is true. You'll see one of the tests which I'll share next week. By the way, I shared a test this week, which you're supposed to do by next Saturday. We'll discuss it next Saturday. I was I wanted to share it 2 days earlier, but I don't know. I mean, I worked on it, I completed it, then I forgot to share it. So I shared it today. So you do it and we'll discuss it next Saturday. And before next Saturday, I'll share another test for you guys. Coming back to the topic at hand. So the number of vectors in a basis has to be n, whereas number of vectors in a spanning system has to be greater than n. Now, another requirement is that the vectors in a basis, they need to be independent. Whereas for a spanning system, you can extract a basis from it. You can extract a basis from a spanning system. So for example, if you have these 4 vectors as the spanning system, then you can take out v1, v2, v3 as a basis. And then v1, v2, v3 are going to be linearly independent. They are going to be independent vectors. They are going to be independent vectors. Okay. Whereas v1, v2, v3, v4 together are not independent. Because you can see here that v4 is basically v1 plus v2. So they are not independent. So the basis vectors are going to be n independent vectors. And a spanning system is going to be n independent vectors plus maybe some extra vectors. May or may not be there. So that's a spanning system. Okay. So that's always correct. A basis is always n independent vectors. A spanning system is a basis plus some additional vectors. So that's a spanning system. Now, obviously, this thing about independence keeps coming up again and again. So let us just complete. Let us look at what is independence. So a system of vectors is linearly independent if the linear combination of the vectors sums to null only when all the scalars are 0. So summation alpha I vi is equals to 0 if and only if alpha I is equals to 0 for all I. Okay. So take the same 4 vectors which I was talking about, v1, v2, v3, and v4. Okay. So my v1 vector is 1, 0, 0. v2 vector is 0, 1, 0. v3 vector is 0, 0, 1. And v4 vector is 1, 1, 0. Let's focus on these 3 vectors. So I want lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 to be equal to 0, which implies that lambda 1 must be equal to lambda 2 must be equal to lambda 3 must be equal to 0. Okay. Because when I add these 3 vectors, the linear combination becomes lambda 1 times 1, 0, 0 plus lambda 2 times 0, 1, 0 plus lambda 3 times 0, 0, 1. So that basically becomes lambda 1, lambda 2, lambda 3, which is equal to 0, 0, 0 only if each of these things is 0. So all the 3 scalars need to be 0 for the linear combination to be. But now if I take all the 4 vectors, then lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 plus lambda 4 v4 is going to be, okay, lambda 1 times this plus lambda 2 times this plus lambda 3 times this plus lambda 4 times. So if I look at the first coordinate, it's going to be lambda 1 plus lambda 4. The second coordinate is lambda 2 plus lambda 4. And the third coordinate is just this one. So lambda. Now this must be equal to 0, 0, 0. So now what I get is that lambda 3 must necessarily be equal to 0. But lambda 1 plus lambda 4 must be 0. So lambda 1 can be equal to minus lambda 4 and lambda 3 must also be equal to minus lambda 4. So you can take lambda 1 equals to lambda 3 equals to minus lambda 4. So you can take lambda 1 as 1, lambda 2 as, lambda 2 must be equal to minus lambda 4. So 1, 1, 0, minus 1. So this is also going to give me a 0 vector. 1, 1, 0, minus 1. So now this summation lambda I vi, it can be 0 even if not all lambdas are simultaneously 0. Okay. So this tells me that the vector v1, v2, v3, v4 are not linearly independent, which means that they are linearly dependent. Now focus on this equation. This same thing can be written as v1, v2, v3, v4 as a matrix times lambda 1, lambda 2, lambda 3, lambda 4 is equals to 0, 0, 0, which is basically ax equals to 0 format, where A is formed by taking the vectors v1 to vn as column vectors. Okay, so if I just generate this A vector as 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 0 times lambda 1, lambda 2, lambda 3, lambda 4 is equal to 0, 0, 0. Then I'm saying that not all lambdas need to be 0. That is what I'm saying here, right? That not all lambdas need to be 0. You can get solutions where lambdas are non-zero. So lambdas non-zero means that this, in this ax equals to 0, this x vector can be non-trivial. Now x vectors used to form the null space. So in this definition, all x which solve the system of equation ax equals to 0 belong to the null space of A. So what I'm saying is that the null space of A, when the vectors when the column vectors are linearly dependent, the null space has vectors other than the 0 vector. Okay, so there are two possible situations here. So this is what I want to summarize for today. Two possible situations for null space. Okay. So null space of A, it can be just the 0 vector, or it can have vectors other than 0 vector. So it has just the 0 vectors in it when the column vectors vi are linearly independent, and it will have vectors other than 0 vectors when the column vectors vi are linearly dependent. So there's a very nice relationship which is happening between linear independence and null space. If the column vectors are linearly independent, then the null space will have just the 0 vector. But if they are linearly dependent, then the null space becomes something larger than the zero vector. So let me come back to this example which we did earlier. This v1, v2, v3, if you remember. I generated v3 as v1 plus v2. So the initial vectors were just v1 and v2, which were linearly independent. So when I tried to solve ax equals to 0, I saw that this has only x equals to 0 as the solution. So this was only the trivial solution. But when I added a new vector v3, which made these things dependent, now the vectors are dependent on each other. So you start getting solutions other than the trivial solution. So all vectors of the format t and minus t can now be the solutions. So the important thing to remember here is that the null space will have only the zero vector if the column vectors are linearly independent, and it will have vectors solutions, basically solutions other than the zero vector if the columns are linearly dependent. Okay.